I will start. Okay. Okay. So our topic for today is wind energy. Okay. So for our content, we will start by talking about some background information about wind energy. We will then go into the history of wind energy, then the science of wind turbines, a cost structure for wind energy. Then we will talk about a bit about offshore wind farming, comparing onshore and offshore wind turbines, and then some improvements and the future of wind energy. So for our background information, it includes first some fossil fuel consumption, and then the shift towards renewable energy and some wind energy overview. Okay, so for the fossil fuel consumption, over the past decade, the economy's dependency on fossil fuel has been increasing at an alarming pace. Humans have been burning fossil fuels to drive their cars, power their businesses, and light their houses. However, it has been also known that these fossil fuels cannot cause many environmental problems and are leading source of the Earth's global warming crisis. So fossil fuels are non-renewable resources formed from the fossilized buried remains of animals and plants. They include coal, crude oil, and natural gas, and they have a high carbon element. So even though fossil fuels create a massive amount of energy, they also bring many environmental harmful effects, such as global warming. So when we burn fossil fuels, we are driving the current climate change crisis. This burning produces large amounts of carbon dioxide that traps heat in the atmosphere and lead to a change in the Earth's climate. This is for the climate change. Another type of harmful consequence is water pollution due to coal mining operations that wash acid runoff and discard large amounts of rocks and soil into streams, rivers, and lakes. Oil leaks and spills are also a harmful effect due to fossil fuel consumption, and it is mainly due to the extraction and transportation process. An example of oil spills and leaks would be the explosion of a drilling platform in the Gulf of Mexico in 2010, which killed 11 people and spilled around 139 million gallons of oil in the ocean. Other types of harmful outcomes include land degradation due to the extraction process of fossil fuels and the emission of harmful air pollutants such as benzene, carbon monoxide, nitrogen oxide, as well as sulfur dioxide, which contributes to acid rain. So, due to all of these harmful effects and the fact that we will sooner or later run out of fossil fuel, our world is slowly but surely shifting toward a cleaner type of energy, renewable energy. One second. Here in the graph on the right, we can see how our fossil fuels, reserves are drying out with time, and we can see that with the pace that we are currently in terms of fossil fuel consumption, oil will run out approximately in 2050, gas in 2060 and coal in 2090. Okay, so since energy is essential to our society and economy, and fossil fuel has shown to be a non-reliable source of energy, we have found that it would be more feasible to produce heat and electricity from renewable resources. And as seen in the graph above, renewable energy has been slowly but surely replacing our fossil fuel needs. So we can see how fossil fuels from 2010 to 2017 have decreased, and all renewable energies approximately have increased, and most of it has been solar energy, with wind energy also staying consistent throughout the years. So renewable energy includes solar energy, hydroelectric power, geothermal power, and biopower, nuclear power, and wind energy. It has also been found that the cost to implement these technologies used to produce renewable power has been decreasing drastically over the years, as seen in the graph below, with solar power seeing the biggest decrease in cost from $350 per megawatt hour in 2009 to $50 per megawatt hour in 2017, and wind energy still being the cheapest source of renewable energy at $45 per megawatt hour. In addition to the benefits towards the environment, this decrease in cost only help reduce the gap between fossil fuel consumption and clean energy use. And now for our wind energy overview. In order to understand the process and use of wind power, we will first try and understand the concept of wind. So as the sun's radiation heats Earth's uneven surface, hot air rises and cool air replaces it. This difference in pressure and temperature creates a kinetic motion-based type of energy, the wind that we know and feel most days of the year. This means that wind power is technically a form of solar energy, and a good example of this would be at the coast near the ocean, where hot air over the land rises and the cold air over the sea replaces it. This allows us to feel the breeze from the sea. Wind turbines then capture that kinetic energy by the rotation of the blades that in turn allow a generator to convert that energy into mechanical power. Now for some advantages of wind power. In addition to the fact that wind energy production does not pollute our environment, wind energy is a native energy because of its availability just about everywhere on Earth. So this fact contributes to reducing energy imports, increasing local employment, and reducing the use of fossil fuels. Wind has also proven throughout the years to be one of the most, if not the most efficient renewable source of energy compared to other renewable energy. It releases less CO2 to the atmospheres and create more energy overall. It has been proven that wind turbines can generate the same amount of electricity per kilowatt as about 48,000 solar panels. So wind energy is one of the most effective types of renewable energy.
Yeah.
This one you can.
So from now we'll continue talking about the history of wind energy. So in this part of the slides, we'll see how it evolved according to the scientific and technological advancement that were available at the time. So first, it is believed that energy was first introduced in Mesopotamia 5,000 years before Christ, where people made use of the power of wind to propel their boats along the Nile River. So it was the first time wind energy was introduced. Then, 100 years before Christ, the wind-driven wheel was invented, and it was created by an engineer, a Greek engineer in the city of Alexandria, in Egypt nowadays. So after that, for the next thousands of years, what we know is that in the most part of the world, windmills were spinning. So you were spinning using wind energy, blowing, so using the wind energy to grind corn and flour. So it was the main purpose of using wind energy. Before it is until 1887 that the first wind turbine was invented by James Bliss, a Scottish professor in Anderson's College. So it was in Glasgow. So he installed his invention in his own garden and used it to power its house. So it was the first time ever that electricity was being supplied by wind power, and that was in 1887. Then in 1895, Paul Lacour, a French inventor, was the first one to convert a windmill into a prototype, so into electrical power to supply the nearest villages with electrical current. So also Paul Lacour also discovered that wind turbine with fewer blade spin faster and more efficient. So this was very important and we'll see that this theory could be used in improving the way the efficiency of our turbine. So we'll be covering that later on in the slides. So next slide now. Okay. So also what we know is that in 1927, the Jacob brothers opened up the first factory to produce commercial wind turbine that were essentially installed on farm that did not have access at the time to an operating electrical network. That was in 1927. In 1931, the vertical axis and horizontal axis wind turbines were created, and they are very similar to the type of wind turbine that operates nowadays. So they were a very essential invention at the time. Then in 1975, NASA introduced a very important and crucial program seeking to develop the first utility scale wind turbine. So 1975 marked a major turning point in the global history of wind energy, where a great number of advanced technology were developed. So great number of advanced technologies related to the wind energy field were developed as part of this program in 1975. And following up to this program in 1988, the cost of production of electrical energy using wind power reached a value of $0.38 per kilowatt hour, which is a very affordable price that marked the rise of wind energy that became a more commercial and accessible type of energy. So that was in 1980. After that, next slide. Yeah, so in 1991, the first offshore wind turbine was constructed in Denmark. We'll be discussing offshore wind turbine later on in this presentation. So we'll be going through them in details. In 2007, the United Kingdom launched a national operation to install thousands of offshore wind turbines all over the country and seek to and their objective was to secure electricity using wind energy for every home in the kingdom by 2020. Of course, this goal wasn't reached in 2020, so last year, but that was their initial objective in 2007. In 2009, like Jawad discussed it, so we have so the economy depended heavily on fossil fuels, and this consumption reached a very high alarming rate. So world government had to take actions. So they pushed further. So they tried to look into renewable energy now. So and wind energy was part of this way of thinking, like to go into more renewable energies. And what we know that in 2013, surprisingly, let's say, China became the world's biggest wind energy producer, passing the United States. So that was the history part. From the history part, we'll be moving on now into the physics of wind turbines. So we'll be seeing how a wind turbine operates. So we'll be discussing the mechanisms of wind turbines. So next slide. So here it is. This is a wind turbine. So we have all the parts that compose a wind turbine, and we'll be discussing each part alone in detail. So so next slide. So in this slide, Jawad talked about, we have the wind resources, which are very important. So he talked about the availability of wind resources. So wind carries a kinetic energy. So the energy carried by wind is of a kinetic form, and it is equal to half mv square, m being the mass of air, and v the speed at which air is diffusing. So this is it. So the wind, so how it's operate, the wind strikes the blades of the wind turbine. So when the wind strikes the blade, the blade spins. So striking the blades, so we know that there will be some kinetic energy that will be arriving at the tips of those blades. This kinetic energy arriving at the tip of those blades is equal to 1/2 rho a v delta t v square. The area of the blade a, it's equal to the area, like the swept area of the blade of the turbine. Delta t is equal to the interval of time, and rho equal to the density of air. So if we multiply it, av delta t, so what we'll get, rho av delta t is the mass basically times v square. So here it is, delta E 1/2 rho AV delta V squared. So we can see it on the side, the equation of kinetic energy that is reaching the blade. Consequently, we can divide this energy by time and get the power equal 1/2 rho AV cube. So when the blades rotate, the blades of my turbine are connected to a rotor. So also the rotor rotates, so it can convert the kinetic power into mechanical power due to this rotation. So according to the mechanical power is equal to PM CP PW. So CP is the aerodynamic power coefficient. So this is a very important equation. So we can see that from PW, uh, so the wind power that is stored in the blades, how much of it is converted to actual mechanical power by the rotor, and this depends on the CP, my aerodynamic power coefficient, which so we can see also that CP is a function of delta of theta and a ratio sigma. So we'll be seeing in the next slide. So we can move on to the next slide now. Okay, so now we have the previous slide. Yeah, so we'll stay at this slide. Sorry, there was a lag in my connection. Okay, so now I said we have my mechanical power equation, which is a function of power coefficient times PW. CP is a function of delta lambda. So basically in this equation, the whole equation, my rho is the same. R is the turbine rotor radius. So I have those two. V is the wind speed. And what I want to know is what my CP, my aerodynamic power coefficient. So what are the variables that make the CP? So let's go to the next slide. Okay, so my CP is equal my CP is a function of theta and lambda, like I said. Lambda theta. Let us start first with theta, which is my pitch angle. That's the angle at which the blade is set with respect to the plane of rotation. So in other terms, the angle being measured between this plane and a straight line from one edge to the blade of the blade to the other in a direction perpendicular to its radius. So this is theta, a design parameter I should be looking for when designing my turbine. And we have also the tip speed ratio lambda. So by definition, here it is in the slide, the equation of lambda, which is RW over V. So R is the radius, V is the wind speed, and W is the rotational speed of my blade. So how can I define this CP according to theta and lambda? I have this graph at the left. So what we do is plot CP for various theta. So we set, for example, theta at 0, 10, 15, 20, 13. Then we vary our lambda, which are W over V, and plot my CP. And as I can see in this graph, so I know that I want the higher CP in order to extract the most power out of my wind power. So I want to maximize my mechanical power extracted. So I want to have to work with the higher CP. So at the graph showed on the left, my CP max is for a theta of 0 to 10 degree and is obtained, and the higher value on this 0, 10 degree graph is obtained for an optimal lambda. So what we can know from this graph is I should be designing for a theta of 0, 10 degree and an optimal lambda of around 8. So for example, if I have R, for example, so I know what V could be, the speed of my wind. So I should be designing R in a way so that this lambda equal 8, this optimal lambda 8 is achieved. So my CP max is achieved. Next slide. Okay, so now from the rotor, so the rotor is connected, so the rotor is rotating. So this rotor is connected to my low speed shaft. I want a higher speed, so through a gearbox, I connect my low speed shaft to a high speed shaft. And I know, and this high speed shaft rotating at between 1000 and 1800 RPM drives a generator that convert the mechanical power extracted from the rotor into electrical power. So here it is the process. I'm going from a rotor to a high speed shaft using a gearbox. Now next slide. Okay, now this drivetrain generator mechanism. So from the moment so this mechanism, the rotor gearbox generator system is defined by the following equation. So these are those two equations. I won't be going into the details, but those are the main equations. So and all the variables I defined. So what I'm interested in is coming up with this W dot G, which is the rotation speed of my the rotation acceleration, because it's derivative of my speed of my generator. So to do that, I need to find my turbine torque TT according to this experience, turbine according to this equation, which is also dependent on my CP, P, R, V, all variables that were previously defined. I need to also measure the TG. So it's the generator torque, which is measured by a dynamic rotary torque sensor. So there is not equation defined here. I need to use a sensor to measure TG, and from that I can calculate my total electrical power extracted, PG equal TG times WG. So here it is. I can find my PG, electrical power extracted. Next slide now. Okay, so we discussed how can I extract from my wind power. So what in summary, let's say we have kinetic power stored in wind. I extract it, convert to mechanical power. Then from mechanical power, I can convert it using a generator to electrical power. Also, there are other components involved in the turbine. There is what we call the anemometer, which is a device that measures the wind speed and transmit the collected data respective to the controller. So let's have a look at the graph. Let's have a look at the graph on the right here. So so the anemometer will send a message to my controller to see. So let's explain this graph. So at very low wind speed, the blades cannot rotate, so electricity cannot be produced. So therefore, the controller will only start up the wind. So will only start up the machine when the anemometer measure a cut-in a speed called the cut-in speed of wind between 3 and 4 milliseconds. So here on the graph we have the cut-in speed 3.5, and will turn off. And this the wind turbine will turn on until the machine. So until I have the anemometer measures a speed of 25 meter per second, which I defined at my cutout speed. So I want the so I will only operate. I want to try to only operate between a 14 meter per second and a 25 meter per second. Using my anemometer, I can know when this speed is I pass this reach to cut off my machine. So so this is done because I don't want to damage my blades when they are rotating at a higher speed. I may damage my wind turbine, so I want to shut it off before going up before going out of the 25 meter per second limit. So here it is the graph. Also, I have a wind vane, which is a sensor also that will measure direction of my wind and turn rotate my turbine accordingly to reach to extract in a more efficient way my wind. So here it is. Okay. Also, we have a brake compartment in the turbine. The brake compartment is placed in case of emergencies. If I want to stop, so I can stop my wind turbine whenever I want. And all those parts we discussed, like all those parts, are contained inside what we call a nacelle that sits atop of a tower. So all of that composes what we know at the wind turbine. So we can go to the next slide and see how it is. So we discussed all of these components and see some the equation that govern the wind turbine. And here we can see it clearly on this graph. All the part I discussed about, they are represented here in this picture. So here it is. Okay, from here we'll be moving into the cost structure of this wind turbine I described. So what are the cost structure involved? So next slide, please. First in this graph we see a trend like between 2010. So first of all, the green column is for onshore turbine, where the blue one is for offshore wind turbine. We're discussing them in details next in this slide. So we can see the decrease of decrease of cost between 2010 and 2019. So this is very clear. We can see that wind electricity production using wind energy is becoming more and more commercial, accessible, cheaper. So that's what we can see. Second point is that the offshore wind turbine is more expensive than the onshore wind turbine. We'll be discussing that in details also when talking about onshore offshore turbine. Next graph. So 75% of the cost of my wind turbine is related to we call the cost structure. So we call the installation cost. So at the price of the turbine itself, and 25% is of my cost is related to operation and maintenance. So the 75% of my turbine cost, of my price cost of my turbine, so my installation cost are distributed according to the following parts. So for example, tower is 26% of the 75%. No, it's 26% of the this installation cost, which constitutes 75% of my total cost structure, and rotor blades 22. And these graphs can tell us what those parts represent in terms of percentage share of total cost. So we have it. It's a cost breakdown of my wind turbine. Okay, those were the two graphs I needed to explain. Next.
Okay, so now we're going to go into detail about offshore wind farming. So the amount of power and electricity produced depends on the available wind speed, which also varies significantly and depends heavily on the hour of the day in which it hits, and also according to the location of the turbines. In general, wind is much more consistent and blows much faster on sea compared to land, and in wind farming, more wind equals more power. So compared to traditional onshore wind farming, the concept of producing electricity from offshore winds is quite new. And the only countries that have working onshore wind farms are the UK, Denmark, Germany, Belgium, Netherlands, and China, with the United States having more than 8 offshore farms under construction. So even though placing wind turbines in seas and or in ocean in seas or oceans produces more power than placing them on land, many other factors come into play before switching to offshore farming, such as cost, transportation, construction, and many more. So here in the next slide, we're going to go into details about onshore and offshore farming and compare the following criteria. So infrastructure, operational maintenance, efficiency size, and environmental effects. For the infrastructure of the wind turbines, compared to offshore wind farming, onshore wind turbines are much easier and less expensive to install. Offshore wind farms require a lot of investment at first place, and in order to start the construction process, it is also much easier and less polluting to transport wind structures if they are installed near the manufacturing plant. Concerning the operation and maintenance, offshore wind turbines are usually more complex. Offshore winds and waves allows turbines to endure more wear and tear. This increases the operation and maintenance costs. Also, since offshore wind farms have limited access, it is harder for technicians and engineers to reach them in order to fix any problem. This means that it would take more time and money to reach offshore wind farms and fix maintenance-related problems. Concerning the efficiency, we already said that higher wind speeds result to higher outputs in terms of electricity generated. So wind is more consistent and blows faster on sea. This allows wind turbines to be much more efficient offshore. And since offshore wind speeds are also far more unpredictable than offshore, this affects the overall performance of onshore wind turbines. Concerning the size of the turbines, offshore wind turbines can be much taller and bigger in size due to the large open space they are sitting in, and this allows more energy to be collected and turned into useful applications. This is also helpful for the construction of huge wind farms that would be impossible to construct on land. Finally, for the environmental effects, the only known effect to the environment caused by wind turbines is noise pollution. And this factor is now being taken care of and taken into consideration before construction begins. And onshore wind farms are now being built far from residential areas. But offshore wind farms can avoid this inconvenience completely since they are built kilometers away from land. However, one of the disadvantages concerning the environmental effect for offshore wind turbines is that marine animals could be affected by the construction. Okay. Now we're going to go into details about the improvements and future of wind energy. So from our previous analysis, it has become clear to us that in order to catch up with fossil fuel consumption, wind turbines need to produce more power, and hence offshore wind farming is the way to go. However, one of the main constraints of offshore wind turbines is the fact that they cannot be built in deep waters. All major offshore wind farms that are operating right now have built their foundations in shallow waters, with only few prototypes of wind turbines being built in deep waters, such as in Scotland and Japan, but they are only prototypes. However, a lot of research and testing is currently being done in order to be able to harvest the winds of deeper water, and the following factors need to be taken into consideration. First, the fixed foundations, the floating foundations, and the rotor design. First, we're going to talk about the fixed foundations. So to this day, the majority of offshore wind turbines are placed on fixed foundations, and more specifically, monopiles and jackets. Monopiles are single cylindrical structures that carry the wind turbines at a depth of around 30 meters. These structures are relatively cheap and easy to build in shallow waters, which is why they are the most widely used structure for offshore wind turbine foundations. Another technique is placing the wind turbine on a jacket, where the tower is built on a platform supported by a series of cylindrical structures at a depth of around 40 meters. These structures, they are normally used in the oil and gas industry, and they can go deeper in the ocean than monopiles, and they ensure stability. There are many other types of foundations used today, such as tripods, which are similar to jackets. They also go 40 meters in depth, and they are very effective in extreme cases such as hurricanes, typhoons, and others. We also have the gravity-based structure that goes 30 meters in depth. It also derives stability from its own weight, but requires excavation and refilling during the construction phase. So, in conclusion, even though all of these structures are reliable and give solutions for winds in shallow waters, they all fail and are extremely expensive to build in deeper seas. Concerning the floating platforms of the offshore wind turbines, it consists of turbines that are held by secured lines attached to anchors in waters deeper than 50 meters. Since most of the seas in the world go deeper than 50 meters and currently used techniques and technology are not economically viable, floating foundations are taking the lead in harvesting deep water winds. So these floating platforms also make the construction and installation process much easier, since they can be transported out to sea fully constructed. And this is surely simpler and less costly than transporting and embedding foundations in seabeds from scratch. Also, this concept helps the inspection, maintenance, and replacement processes, as they can be easily transported without having to disassemble the parts. And another benefit is the availability of stronger winds. Obviously, the deeper we go into the ocean, the stronger the winds are. And this requires manufacturers to build larger wind turbines in order to catch more air and consequently generate more power. Also, the entire wind turbine, if it is built on a floating foundation, it can move vertically flowing with the waves, or even in pitch, tilting against or with the winds, which would allow to catch more kinetic energy from the wind. Now we're going to go into details about the different types of floating foundations. We have the spar buoy platform, which consists of a floating cylinder with a low water plane area, balanced in order to keep the center of gravity below the center of buoyancy. So the support is kept in place using mooring lines and suction anchors. It is a relatively simple design, and it can be done at a low cost of installation, but it can only be accomplished in deep waters. Our second option is the semi-submersible platform, or spar submersible. So this method consists of three large columns connected together by a submerged flat-bottomed canoe. It can be seen in the middle here in the picture. So the canoe provides buoyancy to the foundation, and the columns provide hydrostatic stability. And just like the spar buoy, the structure is kept in position by the mooring lines and the anchors. And some of the advantages of this technique includes low installation costs, transportation to site using standard towing systems, so they don't need an extremely complex towing system to do operation and maintenance. And also the fact that the fully equipped platform, including the turbine, can be transported from and to the site. Disadvantages include the larger structures in comparison to other methods, and the complex design and fabrication process. And for our final design, it is a tension leg platform, and it consists of a highly floatable foundation that has a central column and arms connected to tension tendons. It ensures stability. It has a low mass and can be assembled on shore. However, this type of foundation is harder to keep stable during transportation and installation than other techniques, and its installation is costlier than the previous stated methods. Okay, so with innovative foundations such as floating structures, we can also ask ourselves if we should come up with an innovative design for the rotor. We will consider some of these designs. We have the vertical axis rotor, which Antoine already talked about a bit in the history of wind energy. They have their main rotor shafts perpendicular to the direction of the wind, and they do not need to be pointed towards the hitting wind's direction. And this allows us to dismiss the mechanisms that usually allow turbines to sense wind direction. So, in whatever direction the wind is hitting, the turbine, the vertical axis turbine can capture the kinetic energy from the wind. Also, vertical axis turbines can be placed closely in wind farms, and this increases the power output significantly. However, these rotors experience challenges in the dynamics of their blades due to the rapid variation of the angle of attack, which allows the blades of the turbine to be prone to fatigue. Our second option is the two-blade downwind turbine. This application benefits of a cheaper construction cost, as less material is needed to construct the blades. In addition, removing the third blade makes the turbine much lighter and allows the placement of the rotor lower on the tower, and we can hence capture some downwind from this action. Disadvantages include the dynamic imbalances between the top and bottom blades that cause problems with yawing and puts extensive wear on the bearings. Our last design is the segmented ultralight morphing rotor, which is a relatively new design concept for wind turbines that is capable of producing up to 13 megawatts of power. This design uses a downwind two-bladed coned rotor with blade lengths of over 100 meters. So traditionally, three-bladed horizontal axis wind turbine, they face struggles and challenges on a larger scale. So we cannot build huge blades from horizontal axis wind turbines. With this technique, as we increase the size of the structure, the blades become more flexible in general, whatever rotor design. Especially if we are operating it upwind, they can curve backwards and hit the tower. But with this technique, the segmented ultralight morphing rotor, it is possible to build
Jawad, I should open a new meeting to continue, okay?
Oh, yes, it's okay. Okay.
Yeah.